The forest is busy with information, leaves trembling in layered greens, shafts of light breaking and reforming as clouds drift overhead, branches crossing and uncrossing like slow gestures, and somewhere within that dense visual noise stands a stick insect, perfectly visible and yet functionally non-existent. It is not hidden behind bark or buried beneath foliage. It is fully exposed, occupying open space. The invisibility comes from something more unsettling than concealment: alignment. Its body does not interrupt the scene because it obeys the same visual rules as everything around it. Shape, color, texture, posture, even the angle at which it pauses, all echo the surrounding twigs so precisely that the visual cortex dismisses it as irrelevant background. Nothing about it triggers alarm, curiosity, or recognition. The insect is not overlooked. It is actively filtered out. This filtering is not accidental. The stick insect's survival depends on exploiting the way predators process information. Birds, lizards, and small mammals do not scan forests for every possible object. They scan for anomalies, edges that do not belong, movements that break rhythm, shapes that conflict with expectation. The stick insect's body is a long, segmented cylinder with subtle nodes and ridges that mirror the growth patterns of woody plants. Its coloration is not simply brown or green, but unevenly mottled, with gradients that resemble sun-aged bark or fresh shoots depending on species and habitat. Even its surface reflects light in the same muted, matte way as plant material, avoiding the glossy sheen that might betray living tissue. In ecological terms, this is not camouflage as decoration. It is camouflage as behavioral contract. The insect agrees to follow the rules of the forest, and in return, the forest agrees not to notice it. Movement discipline is where this contract becomes most fragile. A stick insect can remain motionless for hours, sometimes for days, holding a posture that aligns with the angle of the branch it occupies. This is not passive stillness, but controlled muscular tension, an energy-expensive act that prioritizes survival over comfort. When it does move, the motion is deliberate and segmented, broken into pauses that mimic the sway of vegetation under wind. Each step is slow enough that it registers as plant movement rather than animal locomotion. Even the timing matters. A sudden shift during still air is dangerous, while the same movement during a breeze dissolves into the larger choreography of the forest. The insect is not simply waiting, it is listening with its entire body, responding to changes in light, vibration, and airflow. Position choice is a science refined through millions of years of selection. A stick insect does not climb randomly and hope for the best. It seeks branches whose thickness matches its own body diameter, whose coloration complements its cuticle, and whose orientation allows its limbs to extend without breaking silhouette. Some species preferentially align themselves at slight angles rather than horizontal or vertical, matching the irregular geometry of natural twigs rather than the clean lines of human intuition. Shadows are just as important as shapes. The insect positions itself where dappled light fractures its outline, allowing legs and antennae to dissolve into shadow bands. In open sunlight, even perfect mimicry can fail, as sharp shadows reveal depth and volume. In filtered light, the insect becomes two-dimensional again, reduced to pattern rather than form. The risk is constant and unforgiving. One wrong movement breaks the illusion instantly. A leg lifted too quickly, an antenna twitching out of rhythm, a shift that casts a shadow where none should be. Any of these can collapse the deception. Predators do not need prolonged scrutiny. Many rely on rapid visual confirmation, a brief moment where something moves unlike the world around it. When that moment occurs, the response is immediate and often fatal. The stick insect has no venom, no speed, no armor capable of resisting a determined bite. Its defense is singular and absolute. Do not be seen. Failure does not result in injury or retreat. It results in removal from the gene pool. This pressure has shaped not only appearance and behavior, but physiology. Stick insects possess elongated limbs with joints that allow them to lock into position, reducing muscular fatigue during extended stillness. Their metabolism is adapted for low activity, conserving energy during long periods of immobility. Some species can regenerate lost limbs over successive molts, a slow insurance policy against partial detection, where a predator grasps but does not fully secure the insect. Even reproduction reflects invisibility. Eggs often resemble seeds, dropped to the forest floor where ants may carry them into nests, unknowingly providing protection and dispersal. The next generation begins life already embedded in deception, mistaken for something inert and uninteresting. Predator-prey interactions involving stick insects are studies in perception rather than pursuit. Birds perch nearby, scanning branches with eyes tuned for contrast and motion. Reptiles freeze and flick tongues, sampling chemical cues that may or may not betray the insect's presence. Even when a predator looks directly at a stick insect, recognition is not guaranteed. The outline does not resolve into prey. The brain hesitates, and hesitation in a forest full of competing stimuli often means moving on. This is not foolproof, but it is effective enough. The stick insect survives not by overpowering enemies, but by exhausting their attention. There is a subtle irony in how much effort is required to appear effortless. What looks like passive blending is an active, moment-by-moment negotiation with the environment. The insect must continuously reassess its position as light shifts, as leaves fall, as branches sway. It is engaged in constant micro-decisions that never register as intelligence to an outside observer, yet demonstrate a deep evolutionary understanding of visual systems not its own. The forest is not just a place it inhabits, it is a pattern it participates in. Over evolutionary time, this strategy has diversified into extraordinary forms. Some species mimic moss-covered twigs, complete with textured growths along their bodies. Others resemble fresh green shoots, complete with lighter tips that echo new growth. There are even stick insects that sway more dramatically than the wind, exaggerating motion to sell the illusion of vegetation responding to airflow. Each variation reflects a specific ecological niche, a particular predator community, a distinct visual background. Mimicry here is not a static costume. It is a localized solution to a localized problem. The cost of this lifestyle is limitation. Stick insects are not fast colonizers of new environments. A mismatch between body form and habitat can be disastrous. They are specialists in a world that increasingly favors generalists, especially where forests are fragmented or altered. Remove the complexity of branches, shadows, and layered vegetation, and the illusion weakens. In simplified landscapes, there is nothing to blend into, and background data becomes foreground instantly. Their survival strategy depends on the richness of the ecosystem around them, tying their fate tightly to the health of forests themselves. In the end, the stick insect's greatest achievement is not its resemblance to a twig, but its mastery of perception. It survives by understanding, through evolutionary trial rather than conscious thought, how other animals see. It exploits the shortcuts and assumptions built into predator brains, turning cognitive efficiency into vulnerability. Where speed, strength, or aggression fail, irrelevance succeeds. The forest remains full of threats, but also full of noise, and the stick insect slips between signals, unnoticed and unprocessed. It does not hide. It becomes background data, and in doing so, it lives. At rest, the owl butterfly barely exists as an animal at all. It clings to the bark of a tree or the shadowed underside of a branch, wings folded tightly together, presenting nothing but a flat, bark-colored surface mottled with grays and browns. Veins run across the wings like cracks in old wood, and subtle speckling breaks up the outline so completely that even a trained eye can slide past it without registering significance. In the filtered light of the forest understory, where contrast is low and visual clutter is high, the butterfly does not announce itself as prey. It becomes part of the scenery, another patch of texture in a world already saturated with visual information. In this mode, it survives by subtraction, reducing itself to something unremarkable, something not worth processing. The forest floor is an unforgiving place for a large butterfly. Predators move constantly through the understory, from insect-hunting birds that patrol trunks and branches to lizards that scan leaf litter with eyes tuned for motion. For an animal with delicate wings and no physical defenses, stillness is not a preference, but a necessity. The owl butterfly's camouflage is tuned specifically for inactivity. Its closed wings lack bright colors entirely, prioritizing irregular patterns that dissolve edges and prevent shape recognition. Even the posture contributes to the illusion, with the insect positioning itself so that the wing surface aligns with the vertical planes of tree bark rather than cutting across them. When it breathes, the movement is subtle enough to disappear within the ambient motion of leaves and shifting light. But this invisibility is conditional. It works only as long as the butterfly remains unchallenged. The moment a predator draws too close, the rules change abruptly. A bird hopping along a branch, a small mammal probing crevices for insects, or a reptile lifting its head toward movement can collapse the camouflage simply by proximity. At close range, texture is no longer enough. Depth, volume, and the faint outline of a body begin to resolve. This is where the owl butterfly reveals the second half of its survival strategy, one that relies not on hiding, but on shock. In a fraction of a second, the wings snap open. What was muted and bark-like explodes into contrast. Two enormous eyes appear where none existed before, dark pupils surrounded by pale rings that mimic the proportions and symmetry of a vertebrate predator's gaze. The sudden expansion of surface area, combined with the rapid shift from camouflage to high-contrast patterning, overwhelms the sensory expectations of the attacker. This is not a gradual reveal. It is an ambush directed outward, a visual strike designed to interrupt the predator's decision-making process. For an instant, the butterfly is no longer interpreted as prey. It is misidentified as something else entirely. These eye spots are not decorative accidents. They are the product of precise evolutionary tuning shaped by predator psychology. Many forest predators rely heavily on rapid visual classification. They make decisions in moments, determining whether an object represents food, danger, or irrelevance. The owl butterfly exploits this speed. The eye spots resemble the forward-facing eyes of birds or mammals, triggering an instinctive hesitation in predators that themselves are prey to larger hunters. The illusion does not need to be perfect. It only needs to introduce doubt. In ecosystems where hesitation can mean exposure, that doubt is often enough to force a retreat or at least create a window for escape. The effectiveness of this startle display depends on timing and context. If the butterfly revealed its eyes constantly, predators would learn to associate the pattern with harmless prey. Instead, the eyes exist only in moments of threat. When still, they are hidden completely. When exposed, they dominate the visual field. This switching between modes is critical. The owl butterfly does not commit to intimidation as a default state. It saves it as a last resort, deploying it only when camouflage has failed. This dual strategy allows it to operate efficiently in a complex environment, minimizing energy expenditure while maintaining an emergency response when discovery is imminent. The wings themselves are biological instruments designed for this deception. The eye spots are positioned to be maximally visible when the wings are fully spread, and their symmetry enhances the illusion of a face. Surrounding patterns amplify contrast, guiding a predator's attention directly to the false eyes rather than the butterfly's body. Some individuals even accompany the visual display with a sudden wing flick or rustling sound, adding an auditory component that reinforces the shock. The goal is not to convince the predator permanently, but to disrupt its behavior long enough for the butterfly to reposition or flee. Escape does not always mean flight. Often, after the initial display, the butterfly drops abruptly into undergrowth or slips sideways into deeper shadow, folding its wings once more and becoming invisible again. The transition is rapid and precise. The predator, momentarily startled, must recalibrate, searching for a prey item that seems to have vanished. In a dense forest, this recalibration can take too long. Attention shifts elsewhere. The butterfly survives not because the predator believed the lie completely, but because the lie bought time. This strategy reveals a deeper truth about survival in visually complex ecosystems. Not all defenses are physical. Some are informational. The owl butterfly manipulates the flow of information between itself and its predators, controlling when it is visible, how it is interpreted, and what assumptions are triggered. In this sense, the eye spots are less about resemblance and more about interference. They hijack instinctive responses, forcing predators into a behavioral loop that favors caution over attack. The cost of this adaptation is trade-off. Large wings make the butterfly more conspicuous when flying, and the energy required to maintain and deploy such structures is significant. The owl butterfly compensates by being most active during low light periods, when contrast is reduced and predators are less effective at visual tracking. Its behavior, timing, and habitat choice all reinforce the same strategy: remain unseen until necessary, then become unforgettable for just long enough to escape. Predator-prey interactions involving owl butterflies often end without physical contact, making them difficult to observe directly. Yet the prevalence of eye spots across multiple butterfly species suggests repeated success. In environments where predators are experienced and selective, purely passive camouflage is often insufficient. Startle displays add a second layer of defense, one that does not rely on strength or speed but on perception and fear. The butterfly does not outrun danger, it reframes it. There is a subtle irony in the effectiveness of this tactic. The owl butterfly survives by pretending to be something it is not, yet that pretense only works because predators themselves are shaped by fear. The same instincts that keep birds alive also make them vulnerable to deception. Evolution does not reward truth, it rewards outcomes, and in this case, the outcome is survival purchased through a momentary lie. When the wings close again and the eyes vanish, the forest returns to normal. Bark looks like bark. Shadows look like shadows. The predator moves on, unaware that it has just been manipulated by a fragile insect with no weapons beyond pattern and timing. The owl butterfly remains, motionless once more, waiting for the world to forget it. In ecosystems governed by attention, sometimes the difference between life and death is not strength or speed, but the ability to control what others think they see. Sometimes escape is bought with a lie. The leopard lacewing enters the forest like a contradiction, its wings catching light in flashes of orange, black, and white that seem far too bold for an animal so exposed. Against the human expectation of camouflage as dullness, it appears almost reckless, drifting through sun-broken foliage with a pattern that announces itself rather than recedes. Yet this impression belongs entirely to the human eye, an eye trained to isolate objects, to lock onto symmetry and color as signals of importance. In the forest canopy and mid-story, where motion is constant and light fractures into restless mosaics, the leopard lacewing does not stand out. It dissolves, not by blending in, but by overwhelming the visual systems of those that hunt it. This butterfly inhabits environments where leaves overlap in dense layers, where shadows slide across surfaces as branches sway, and where the background is never static for more than a breath. In such places, survival is not achieved by becoming invisible, but by becoming unreadable. The leopard lacewing's wings are marked with irregular patches that interrupt its outline, breaking the continuity of form that predators rely on when tracking moving prey. When the butterfly flies, these markings do not register as a single object in motion. They fragment into competing signals, each patch catching and releasing light at different moments, preventing the predator's eyes from stitching them together into a coherent target. For birds, the primary predators of butterflies in these habitats, pursuit depends on predictive tracking. A bird must not only see prey, but anticipate where it will be a moment later. This requires a stable visual model, a continuous outline that the brain can extrapolate forward through space. The leopard lacewing denies this stability. Its pattern creates false edges and misleading contrasts, causing the prey image to break apart under pursuit. As the butterfly weaves through foliage, the patches on its wings align momentarily with sunlit leaves or dark shadows, then disappear again, creating the illusion of multiple moving fragments rather than a single fleeing animal. This is pattern disruption at its most effective, not as static disguise, but as dynamic interference. The wings are not meant to be viewed at rest against a plain background. They are designed for motion through chaos. In dappled light, where brightness and darkness alternate rapidly, the bold colors lose their meaning. Orange becomes leaf glow, black becomes shadow, white becomes glare. The butterfly's form is present, but its identity is not. Predators see movement without clarity, motion without certainty. In the fraction of a second required to commit to an attack, uncertainty is often enough to cause failure. Beauty in this context is not ornamental. It is functional. The patterns that humans interpret as striking or decorative are tuned to visual systems very different from our own. Birds perceive color and contrast differently, often with heightened sensitivity to ultraviolet wavelengths and rapid motion. What appears obvious and high contrast to a human observer may register as noise to an avian eye, especially when layered over the already complex visual field of the forest. The leopard lacewing exploits this difference. Its wings do not aim to vanish, they aim to confuse. Even when the butterfly pauses, wings open or partially closed, the disruption continues. The irregular markings prevent predators from resolving a clean silhouette. Leaves behind and in front of the butterfly merge visually with its wing pattern, flattening depth and erasing the boundary between animal and environment. In certain lighting, the butterfly seems to flicker in and out of existence, not because it moves, but because the background moves around it. Wind stirs foliage, shifting highlights across the wings and causing the pattern to reconfigure moment by moment. Stillness does not restore clarity. It merely changes the terms of confusion. Predator-prey interactions involving leopard lacewings often unfold too quickly for human observers to pass. A bird darts, misses, veers away, recalculates. The butterfly changes direction abruptly, its flight path erratic not because of panic, but because unpredictability compounds visual disruption. Straight lines are easy to follow. Curves and sudden shifts fracture pursuit. Each wing beat reshuffles the pattern, denying the predator a stable reference point. In these moments, the lacewing's survival depends not on outrunning the bird, but on exhausting its ability to track. There is an energetic cost to this strategy. Maintaining bright pigmentation and large wings requires resources, and the butterfly must feed efficiently to sustain it. Nectar sources are selected carefully, and feeding often occurs in brief windows when predation risk is lower. The butterfly's life is a balance between visibility and vulnerability, with pattern disruption acting as the counterweight. Where other species rely on hiding or intimidation, the leopard lacewing commits to confusion as its primary defense. This strategy is especially effective in environments that are already visually complex. In simplified habitats where backgrounds are uniform and lighting is consistent, the butterfly's pattern would be a liability. Its survival is therefore tightly linked to the structure of its ecosystem. Dense foliage, layered vegetation, and shifting light are not just scenery. They are active components of its defense. The butterfly and the forest form a partnership, each amplifying the other's complexity. Remove the chaos, and the illusion collapses. Humans often misunderstand camouflage because we imagine it as a matter of matching colors or shapes. The leopard lacewing demonstrates a more nuanced truth. Camouflage can be about disrupting perception rather than avoiding it. It can function through excess rather than restraint. In a world where predators must make rapid decisions, too much information can be as dangerous as too little. The butterfly overwhelms the visual processing pipeline, turning its own conspicuousness into a weapon. There is a quiet sophistication in this approach. The leopard lacewing does not rely on a single trick or moment. Its entire existence is shaped around how it is seen while moving through space. Flight behavior, wing structure, pigmentation, and habitat preference all reinforce the same outcome: break recognition before it can solidify. The butterfly does not wait for predators to make mistakes. It engineers the conditions that make mistakes inevitable. As it drifts deeper into foliage and disappears among shifting leaves, the lacewing leaves behind no clear memory of its path. The bird that pursued its circles once, then abandons the chase, its mental image of the prey already dissolving. Nothing was hidden. Nothing vanished outright. Instead, the rules of tracking were quietly sabotaged. The leopard lacewing survives not by becoming invisible or frightening, but by refusing to be followed. It does not hide. it scrambles your tracking. In the tall grasses of a sunlit meadow, where stems cross and uncross in slow motion and the air hums with layered insect life, the wasp spider constructs something that looks less like a structure and more like an intervention. Its web does not simply occupy space, it alters it. Suspended between grass blades, the silk catches light in a way that interrupts the visual logic of the field, introducing lines and contrasts that do not belong to the plants themselves. At the center waits the spider, banded in yellow and black, its body echoing the warning colors of stinging insects. Nothing here is accidental. Every strand, every orientation, every visual signal is part of a system designed not only to capture prey, but to shape how that prey perceives the world in the moments before impact. The web's placement is the first layer of deception architecture. Unlike spiders that retreat into dark corners or shaded understory, the wasp spider chooses open, brightly lit environments where flying insects navigate by visual landmarks. The web is often angled to intercept common flight paths, stretched across gaps that pollinators routinely cross while moving between flowers. Grassland insects are creatures of habit, following learned routes that balance efficiency and safety. By positioning its web across these invisible highways, the spider inserts an obstacle into a mental map that has already been rehearsed countless times. The prey does not expect resistance here, and expectation is as critical to survival as reflex. At the heart of the web lies a striking feature, a dense zigzag of silk known as a stabilimentum. Its purpose has been debated for decades, precisely because it appears to serve multiple, sometimes contradictory roles. In certain lighting, the bright silk reflects ultraviolet wavelengths that are highly visible to insects, potentially acting as a warning sign that encourages larger animals to avoid destroying the web. In other contexts, that same reflection may function as a lure, mimicking the visual cues of flowers or open sky that attract pollinators. And under different conditions still, the stabilimentum breaks up the outline of the spider itself, masking its presence against the complex background of vegetation. The web does not communicate a single message. It adapts its meaning depending on who is looking and how. This ambiguity is the core of the wasp spider's strategy. The web edits the scene, altering contrast, depth, and expectation in ways that confuse rather than clarify. A flying insect approaching at speed must make rapid decisions based on limited information. Is this space open or occupied? Is that brightness a gap or an object? Is the pattern ahead part of the environment or something to avoid? The stabilimentum exploits the insect's reliance on simple heuristics, the mental shortcuts that normally allow it to navigate efficiently. In the split second where those heuristics fail, the web succeeds. Once prey enters the web, the deception shifts from visual to mechanical. Vibrations ripple outward from the point of impact, traveling along silk strands that transmit information with remarkable precision. The wasp spider does not rush immediately. It waits, reading the pattern of vibrations to assess size, location, and struggle intensity. Each type of prey produces a distinct signature. A small fly generates rapid, irregular tremors. A larger grasshopper creates slower, more forceful pulses. Even the direction of movement can be inferred from how vibrations propagate through the web's radial and spiral threads. This sensory system allows the spider to decide whether engagement is worth the risk. Commitment is not guaranteed. The wasp spider is selective because not everything that hits the web is safe to subdue. Large or potentially dangerous insects can damage the web or injure the spider itself. By delaying its approach, the spider minimizes unnecessary exposure. This restraint is a form of intelligence shaped by natural selection, favoring individuals that balance aggression with caution. When the spider does move, it does so with precision, advancing along non-sticky threads to avoid becoming trapped in its own weapon. The spider's appearance reinforces the illusion even after contact. Its bold yellow and black patterning mirrors that of stinging wasps, a resemblance that may deter some predators from attacking the spider while it is exposed at the web's center. This is not mimicry in the strict sense, but visual association. Predators that have learned to avoid painful encounters may hesitate, buying the spider time to retreat or drop from the web if threatened. The spider itself becomes part of the warning architecture, a living signal embedded within the trap. Environmental conditions constantly modulate how the web functions. In bright sunlight, reflective silk stands out sharply, enhancing visual disruption. Under overcast skies, contrast softens, and the web becomes harder to detect until it is too late. Wind adds another layer of complexity, causing the web to sway slightly, blurring its outline and further confusing approaching insects. The wasp spider does not control these variables, but it exploits them, building in locations where natural movement amplifies the web's effects. The meadow is not just a setting, it is an active collaborator. What makes this strategy especially effective is its flexibility. The same structure can warn, lure, or conceal, depending on context. There is no single interpretation of the web, only probabilities that shift with light angle, background vegetation, and the visual systems of different species. Humans, with our bias towards static interpretation, often search for a definitive answer to what the stabilimentum is for. In reality, its power lies in refusing to settle into one role. It creates uncertainty, and uncertainty is lethal for fast-moving prey. The web also represents a trade-off. Building and maintaining such a structure requires energy and exposes the spider to predators and environmental damage. Rain can destroy the web overnight. Grazing animals can erase it in an instant. Each day, the spider must decide whether to rebuild, relocate, or adapt. Survival depends on constant recalibration, responding to subtle changes in prey availability and habitat structure. The architecture is temporary, but the strategy is enduring. From an ecological perspective, the wasp spider plays a role beyond individual survival. By selectively capturing certain insects, it influences pollinator movement and local insect populations. Its webs alter flight patterns in the meadow, creating zones of avoidance and risk that ripple outward through the ecosystem. Other insects learn, adapt, and modify their behavior in response. The trap does not exist in isolation. It reshapes the behavior of everything around it. In this way, the wasp spider is not merely a hunter, but a designer of perception. It constructs an environment within an environment, layering signals that manipulate how space is read and navigated. The prey does not simply fly into a web. It flies into a misinterpretation of reality, guided by cues that have been subtly rewritten. The spider waits, patient and still, until the moment when those edits produce a mistake. As the meadow continues its quiet motion and insects trace invisible paths through the air, the web remains suspended, shimmering and ambiguous. It is at once barrier and invitation, warning and deception, background and focal point. The wasp spider does not rely on speed or strength alone. It relies on architecture that reaches beyond silk and into perception itself. It builds a trap that also edits the scene. In the humid margins of forest clearings and along sunlit trails where insects move between feeding and breeding grounds, the golden silk orb weaver stretches a structure that is almost impossible to see until it is too late. The web hangs in open air, spanning gaps between branches with such delicacy that it appears more like a distortion of space than a physical object. Light passes through it with minimal interruption. Shadows do not gather on its threads. To the flying insect, the path ahead looks clear, uninterrupted, safe. The trap does not announce itself. It waits, invisible wire drawn tight across the sky. This invisibility is not the result of absence, but of precision. The silk produced by the golden silk orb weaver is remarkably thin and exceptionally strong, spun in strands fine enough to evade detection by compound eyes tuned for broader contrasts. Many insects perceive the world as a mosaic of motion and color, rather than sharply defined lines. The web exploits this limitation. Its threads reflect light at wavelengths that blend into the surrounding brightness, especially in open, sunlit spaces where glare and scattered reflections dominate. Against a background of shifting leaves and open air, the silk becomes part of the visual noise, indistinguishable from the atmosphere itself. Yet the web is far from fragile. Each strand is tensioned with extraordinary care. calibrated to absorb impact without breaking while transmitting information instantly across the entire structure. When an insect collides with the web, the sensation is not of hitting a barrier, but of sudden resistance where none was expected. Momentum carries the prey forward, entangling wings and legs before reflexes can correct course. By the time the insect registers danger, escape routes are already compromised. The trap succeeds because it violates expectation, replacing empty space with force in a fraction of a second. The spider itself often sits off-center, sometimes several body lengths away from the point of impact, appearing almost incidental to the structure it controls. This distance is deliberate. By removing itself from the visual focal point of the web, the spider reduces the chance of being detected by predators and prey alike. The web does the work. The spider listens. Vibrations travel along the silk faster than any visual signal, carrying detailed information about the size, location, and struggle pattern of whatever has struck the threads. The orb weaver reads these vibrations with remarkable sensitivity, distinguishing between a trapped insect worth pursuing and debris that should be ignored. This sensory system transforms the web into an extension of the spider's nervous system. Each radial line and spiral thread functions as a conduit for mechanical information, allowing the spider to perceive events occurring far beyond its immediate reach. A small, lightly struggling insect produces rapid, uneven vibrations. A larger prey item generates slower, heavier pulses that propagate differently across the web. Even the direction of movement can be inferred from subtle differences in tension. The spider does not rush blindly. It assesses, calculates, and commits only when the odds favor success. Placement is where the golden silk orb weaver turns engineering into strategy. The spider does not build its web randomly. It chooses locations where insect traffic is already concentrated, often across narrow corridors formed by vegetation, trails, or the edges of clearings. Flying insects tend to follow consistent routes that minimize energy expenditure and exposure to predators. By spanning these routes, the spider intercepts prey that is already committed to a trajectory. There is little room to maneuver and no time to react. The web becomes an invisible checkpoint in the airspace of the forest. Height matters as well. The web is often positioned at levels where medium-sized insects fly, avoiding ground-level turbulence while staying below the canopy where larger birds dominate. This vertical precision reflects a deep evolutionary tuning to prey behavior. The spider is not merely casting a net. It is placing a barrier exactly where probability peaks. Each successful capture reinforces the value of that location, and over time, spiders that choose poorly are removed from the population. What remains is instinct refined by countless failures. The golden hue of the silk, visible only under certain angles of light, adds another layer of subtlety. In direct sunlight, the threads may glint faintly, resembling stray reflections rather than solid obstacles. Some researchers suggest that this coloration may even attract certain insects, mistaking the shimmer for floral cues or open sky. Whether lure or byproduct, the effect is the same. The silk does not warn. It misleads. Prey approaches with confidence, unaware that the air itself has been weaponized. Once contact is made, the spider moves with decisive efficiency. It advances along non-sticky threads, avoiding entanglement while closing the distance. Silk is deployed rapidly, wrapping the prey to immobilize it further and dampen vibrations that might attract predators. The entire process unfolds quickly, minimizing exposure. Speed here is not about chasing prey, but about controlling the aftermath of capture. The web has already done the hardest part. There is an irony in how little attention the spider itself draws. Its body may be patterned and visible at close range, but in the context of the web's function, it is almost secondary. The true camouflage lies not in the spider's appearance, but in the weapon it wields. The web does not look like a trap. It looks like nothing at all. Predators scanning for spiders often miss the web entirely, and prey never see it until the moment of collision. The danger is not where the eye expects it to be. Environmental conditions continually test this strategy. Wind can deform the web, altering tension and reducing effectiveness. Rain can weigh down threads or destroy sections entirely. The spider responds by repairing, adjusting, or rebuilding, sometimes daily. Silk production is energetically expensive, and each decision to rebuild reflects a calculation shaped by hunger, risk, and opportunity. The web is temporary, but the principles behind its construction are consistent, honed by selection to balance invisibility with strength. Beyond individual survival, the web influences the movement of insects through the ecosystem. Over time, repeated losses along certain flight paths can alter behavior, pushing insects to seek alternative routes. In this way, the golden silk orb weaver subtly reshapes the aerial landscape, creating zones of higher and lower risk. The forest's airspace is not empty. It is structured by invisible forces, many of them spun from silk. For humans, the web often becomes visible only when light catches it at just the right angle, revealing a sudden geometry suspended in air. There is a moment of surprise, a realization that danger existed unnoticed. For insects, there is no such moment. Recognition comes too late. The web has already closed the gap between perception and reality. In the end, the golden silk orb weaver survives not by hiding itself, but by hiding its intent. The spider remains still, patient and exposed, yet rarely challenged. The true deception lies stretched across the forest's open spaces, rewriting them into lethal boundaries. The camouflage is not the spider. It is the weapon. The praying mantis exists in the margins between shapes, in the layered stillness of shrubs, grasses, and low branches, where leaves overlap and shadows fracture into irregular planes. Its body does not announce itself as an organism. It presents instead as geometry, angles where angles already exist, planes aligned with other planes, a silhouette that belongs so convincingly to the architecture of vegetation that the eye never flags it as separate. This is not concealment through color alone, though color plays its role. This is concealment through structure, through the careful imitation of how plants occupy space. At rest, the mantis adopts a posture that collapses its identity into the background. Its elongated thorax mirrors the stems it clings to, while its folded wings form flat surfaces that resemble leaves held in mid-decay. Veins trace faint lines across those wings, echoing the vascular patterns of foliage. Even the head, with its triangular shape and forward-facing eyes, can be angled so that its profile breaks into nothing more than a notch in the visual clutter. In habitats thick with vegetation, this geometry is everywhere. The mantis does not need to disappear completely. It needs only to avoid becoming distinct. Stillness is the core of this illusion. The mantis can remain motionless for extraordinary lengths of time, its muscles locked in a posture that minimizes fatigue while maintaining readiness. This is not the frozen stillness of inactivity, but a controlled suspension, tuned to the rhythm of the environment. Leaves sway, shadows slide, light pulses as clouds pass overhead. Against this slow, continuous movement, the mantis holds a position that appears static yet natural, as if it too were rooted. Any movement it does make is incremental, adjusted to coincide with wind or shifting light, ensuring that motion reads as environmental rather than intentional. Shadow is as important as shape. The mantis selects positions where its body falls along existing shadow lines, flattening its three-dimensional form into the visual plane of the plant it occupies. In direct light, even perfect mimicry can fail, as depth reveals volume. In broken light, volume dissolves. The mantis becomes an absence defined by what surrounds it, rather than what it is. Predators scanning for prey, and prey scanning for danger, both rely on contrast and disruption. The mantis offers neither. This deception is not limited to passive defense. It is the foundation of an ambush strategy refined to brutal efficiency. The mantis is a predator that does not chase. It waits for the world to come to it. Insects move constantly through vegetation, following chemical cues, visual landmarks, and habitual paths shaped by feeding and mating behaviors. The mantis positions itself along these routes, often near flowers or dense clusters of leaves where prey traffic is highest. It does not lure. It intercepts. What makes the ambush possible is patience combined with sensory awareness. The mantis possesses vision capable of detecting subtle movement at close range, its eyes providing depth perception unusual among insects. This allows precise judgment of distance, angle, and timing. It does not strike at every movement. It evaluates. A prey insect must cross an invisible threshold, entering a zone where escape becomes improbable. Until that moment, the mantis remains inert, a piece of leaf geometry suspended in space. When the strike comes, it is almost too fast to register. The raptorial forelegs, folded tightly against the thorax like hinged blades, unfold in a burst of motion measured in fractions of a second. Spines lining the inner surfaces of these arms snap shut around the prey, forming a cage of living hooks. There is no probing or tentative contact. The grab is decisive and terminal. Escape, once contact is made, is unrealistic. The mechanics favor the mantis entirely. Muscle power, leverage, and timing converge to eliminate reaction time. This speed is not just a matter of muscle strength. It is the result of elastic energy stored in the mantis's limbs, released explosively when the strike is triggered. Tendons and joints function like loaded springs, allowing movements faster than muscle contraction alone would permit. This design minimizes warning. There is no gradual acceleration, no visible wind-up. One moment, nothing happens. The next, the prey is restrained. The prey's struggle begins immediately, wings beating, legs pushing against the spines that hold it. But the geometry that once hid the mantis now becomes a trap. The mantis adjusts its grip with micro-movements, tightening control while keeping its body anchored to the vegetation. Its hind legs brace against the substrate, distributing force and preventing recoil. The prey is pulled inward, closer to the mandibles, where the final phase of the ambush unfolds. The mantis feeds methodically, often beginning consumption while the prey is still alive. This is not cruelty, but efficiency. In the wild, hesitation invites risk. The longer a prey item struggles, the greater the chance of attracting predators or competitors. By immobilizing and consuming quickly, the mantis reduces exposure. Its digestive system is adapted to handle active prey, and its behavior reflects an evolutionary pressure to complete the interaction with minimal delay. What makes this strategy especially effective is how rarely it is detected before execution. Prey insects do not see the mantis as a threat because they do not see it at all. Their sensory systems are tuned to recognize specific dangers, often moving shapes or contrasting colors. A static object that matches the background falls outside their threat model. The mantis exploits this blind spot completely. It does not need to trick the prey into approaching. It simply allows the prey to behave normally. Predators of mantises face similar challenges. Birds and reptiles scanning vegetation may look directly at a mantis without recognizing it. Only when the mantis moves does it risk detection, and movement is carefully rationed. Even then, the mantis can freeze instantly, halting motion mid-gesture and re-entering the background. This ability to switch between motion and stillness without transitional cues is rare and powerful. It allows the mantis to operate in plain sight without being processed as an animal. There are trade-offs. The mantis's reliance on camouflage and ambush makes it vulnerable in simplified environments where vegetation structure is reduced. Open fields, heavily managed landscapes, or areas with uniform plant growth strip away the complexity that sustains the illusion. In such places, the mantis becomes visible, its geometry exposed rather than concealed. Survival here depends on relocation or adaptation, highlighting how tightly this predator is bound to habitat structure. Within healthy ecosystems, however, the mantis plays a significant role in regulating insect populations. By targeting a wide range of prey, including pollinators and herbivores, it influences the flow of energy through the food web. Its presence alters the behavior of other insects, creating zones of heightened risk that ripple outward through the vegetation. The ambush predator does not need to be seen to be felt. From a distance, the scene appears tranquil. Leaves stir gently. Insects drift from stem to stem. Nothing suggests violence or urgency. Yet within this calm exists a predator perfectly aligned with its environment, waiting for a precise alignment of chance and behavior. The mantis does not pursue its prey across space. It waits for prey to cross a line that exists only in its perception. In the final moment, there is no warning, no escalation, no chance to adjust. The geometry resolves into action too late for response. You do not see it. Then you're already grabbed. In a field alive with movement, where grasses ripple and leaves tremble under the weight of insects feeding and fleeing, the ladybug announces itself without hesitation. Its body is small, rounded, almost toy-like in proportion, and its shell gleams with red or orange punctuated by stark black spots. Against the muted greens and browns of vegetation, it is impossible to miss. To a human observer, the impression is immediate and disarming. This is not a creature that looks dangerous. It looks harmless, decorative, even friendly. That reaction is not accidental. It is the first layer of a survival strategy built not on concealment, but on misjudgment. Predators learn quickly in complex ecosystems, but learning requires consequences. The ladybug's appearance exploits a critical gap in predator decision-making, particularly among inexperienced birds and small vertebrates. Bright colors often signal toxicity, yet the ladybug's rounded shape and slow, deliberate movements soften that signal, blurring the line between warning and invitation. For a predator assessing risk in a fraction of a second, the insect does not register as an obvious threat. It is too small, too still, too visually simple. The result is an initial underestimation that the ladybug is fully prepared to punish. Beneath the smooth, glossy exterior lies a form of armor that is both structural and symbolic. The hardened wing covers, known as elytra, are thick relative to the insect's size, forming a dome that distributes force away from vital organs. This shape resists crushing bites and pecking attacks, allowing the ladybug to survive encounters that would be fatal to softer-bodied insects. The dome is not just protection against impact, it reinforces the insect's visual message. Predators perceive rounded forms as less threatening and less urgent targets, a bias that buys the ladybug time during the most critical moment of contact. When that contact occurs, the illusion collapses abruptly. The ladybug does not flee. It does not struggle dramatically. Instead, it deploys chemistry. Specialized glands release a toxic, foul-tasting fluid through the joints of its legs, a process often referred to as reflex bleeding. The liquid is not lethal, but it is potent enough to trigger an immediate rejection response. Birds shake their heads, wipe their beaks, and spit the insect free. Lizards recoil. Small mammals learn just as quickly. The lesson is sharp, unpleasant, and memorable. This chemical defense is not merely a backup. It is the core of the ladybug's strategy. Survival does not depend on escaping every attack, but on ensuring that attacks do not repeat. Predators that experience the taste of a ladybug often remember it for life, associating the bright colors and rounded shape with discomfort. The next time they encounter a similar insect, they hesitate or avoid it entirely. The ladybug benefits not just from its own defense, but from the collective memory of the ecosystem. Each failed attack strengthens the warning for others. The effectiveness of this strategy depends on honesty. The ladybug's colors are not a bluff. They are tied directly to a real consequence. This is known as a posematism, a system where conspicuous coloration signals genuine unpalatability or toxicity. In environments where such signals are reliable, predators evolve to recognize and respect them. Over time, avoidance becomes instinctive. The ladybug no longer needs to be attacked to be protected. Its appearance alone is enough to stop the interaction before it begins. What makes the ladybug's warning especially efficient is its consistency across contexts. Whether resting on a leaf, crawling across a stem, or flying between plants, the colors remain visible. There is no need to switch modes or reveal hidden patterns. The message is always on display. This constant advertisement simplifies the insect's behavioral demands. It does not need to time its movements carefully or seek specific backgrounds. It can afford to be slow, even clumsy, because its defense operates at the level of perception rather than speed. The chemical compounds responsible for the ladybug's defense are derived from its diet, particularly from the aphids it consumes in large numbers. These prey insects often feed on plants that contain toxic compounds, which then accumulate in the ladybug's body. In this way, the ladybug is embedded in a larger chemical network within the ecosystem, recycling plant defenses into its own protection. This relationship highlights the interconnectedness of trophic levels, where the chemistry of plants influences the behavior of predators through an intermediary insect. The ladybug's role extends beyond its own survival. As a prolific predator of aphids and other plant-damaging insects, it exerts significant influence on vegetation health. Gardens, fields, and forests benefit from its presence, often without visible acknowledgement. This ecological service further reinforces the ladybug's success, as environments that support healthy plant life also support the prey populations it relies on. The insect's warning colors become a familiar sight in productive ecosystems, reinforcing predator learning across generations. There is a subtle advantage to being underestimated before being recognized as dangerous. Predators that avoid danger too readily may miss opportunities to feed. Those that sample indiscriminately suffer consequences. The ladybug positions itself at this intersection, inviting a mistake once, then preventing future ones. Its survival strategy is not about avoiding contact altogether, but about shaping predator behavior through experience. One unpleasant encounter can reshape a predator's diet choices permanently. Some species even amplify this effect by clustering together during certain seasons, especially when overwintering. Aggregations of ladybugs create concentrated visual warnings, reinforcing the signal through repetition. A predator encountering a group learns faster and more decisively than it would from a single individual. The cost of one mistake is multiplied, accelerating avoidance learning within the local predator community. This collective strategy further reduces the likelihood of attack on any individual insect. From a human perspective, the ladybug's charm often obscures the sophistication of its defenses. It is easy to project harmlessness onto an animal that looks familiar and benign. Yet this projection mirrors the very bias that predators fall prey to. The ladybug succeeds because it turns that bias into a weapon. Its cuteness is not a vulnerability. It is part of the disguise. In a world where many insects must vanish into backgrounds or strike faster than perception, the ladybug takes a different path. It remains visible, slow, and calm, trusting in a system of signals and consequences refined over evolutionary time. It does not waste energy hiding. It does not need to ambush. It allows predators to see it clearly, confident that seeing is enough. As the insect crawls across a leaf, its shell catching the light, there is no urgency in its movement. The warning is already delivered. The ecosystem has learned. The ladybug does not need to hide if it advertises danger. On the surface of a broad leaf, where sunlight pools and drains with the movement of clouds, the shield bug settles into place and disappears without leaving. Its body is flattened and angular, shaped not like an animal in motion, but like a piece of the plant itself, a living extension of leaf geometry rather than a visitor upon it. The edges of its form echo the contours of the leaf beneath, tapering and widening in ways that feel inevitable rather than designed. Veins run through its wings in muted greens and browns, mirroring the vascular patterns of foliage so closely that the boundary between insect and plant becomes negotiable. In this stillness, recognition fails. The eye slides over the bug not because it is hidden, but because it appears already accounted for. The effectiveness of this disguise lies in restraint. The shield bug does not overcommit to mimicry with exaggerated shapes or perfect coloration. Instead, it approximates the average, the expected, the background texture that fills peripheral vision but rarely demands attention. Its posture reinforces this illusion. When at rest, the shield bug presses its body close to the leaf surface, reducing shadows and minimizing depth cues that might reveal volume. Legs are tucked in tight, antennae held still or aligned along natural lines in the plant. Even its orientation matters. The insect positions itself to match the angle of the leaf relative to the sun, ensuring that highlights and shadows fall where they should. In doing so, it becomes visually economical, offering no new information for a predator's brain to process. This strategy depends on patience. Shield bugs can remain motionless for long periods, waiting out danger rather than reacting to it. Stillness is not passive here. It is an active choice reinforced by physiological adaptations that allow the insect to conserve energy while maintaining readiness. Muscles hold position without tremor, and metabolic rates remain low, enabling the bug to persist in a state of near invisibility even as birds hop nearby or larger insects crawl across the same plant. In a landscape saturated with motion, stillness becomes its own form of camouflage. Predators searching for prey on leaves rely heavily on contrast and movement. Birds scan for shifting shapes, for the telltale twitch of legs or flutter of wings. Herbivorous insects focus on texture and chemistry, distinguishing edible surfaces from threats. The shield bug disrupts both processes by refusing to differentiate itself. It does not move when the leaf moves. It does not stand out when light changes. It occupies the same visual category as the plant itself, and in doing so, it avoids triggering the recognition pathways that would turn attention into action. Yet this invisibility is not absolute. No disguise holds forever in a world governed by chance. A sudden gust of wind may flip the leaf, exposing the bug's underside. A predator may land too close, its head tilting as depth perception sharpens. In these moments, the first layer of defense has failed. The shield bug is seen. What happens next determines whether the encounter ends in survival or loss. Instead of fleeing immediately, the shield bug often remains still for a fraction longer, testing whether recognition has truly occurred. This hesitation is calculated. Many predators experience brief uncertainty even after spotting something unusual, reassessing whether it represents food, threat, or mistake. If that uncertainty persists, the shield bug may still escape without further action. But if the predator commits, the second system activates, one that relies not on vision, but on chemistry. Shield bugs possess specialized glands that produce volatile chemical compounds, released when the insect is threatened or handled. The odor is sharp and penetrating, spreading quickly through the air or coating a predator's mouthparts upon contact. To human noses, it is often described as pungent or unpleasant. To predators, it is worse. The chemicals interfere with taste and smell, creating a sensory overload that makes the shield bug an unrewarding target. The insect does not need to poison its attacker. It needs only to convince it that the effort is not worth repeating. This chemical defense functions as a teaching tool. Predators that attempt to eat a shield bug often release it almost immediately, wiping their beaks or shaking their heads in discomfort. The memory of that sensation lingers. Future encounters with similar shapes and scents are avoided, even if hunger remains. Over time, this learning reduces predation pressure not only on individual shield bugs, but on the population as a whole. The defense is communal in effect, shaping predator behavior across seasons. What makes this system especially efficient is its hierarchy. Chemistry is not deployed casually. Producing defensive compounds requires energy and exposes the insect to attention through scent. By prioritizing stealth first, the shield bug minimizes the need to activate its chemical arsenal. Most encounters end before detection, preserving resources and reducing risk. Only when disguise fails does the insect escalate, adding a second layer of protection that compensates for the first. This layered strategy reflects a broader principle in survival design. Redundancy increases resilience. The shield bug does not rely on a single trick or assumption. It prepares for failure by embedding multiple solutions into its biology and behavior. Shape and stillness address visual predators. Chemistry addresses tactile and close-range threats. Together, they form a defense system that adapts dynamically to circumstance. The smell itself plays a critical role in predator learning because it is difficult to ignore or forget. Visual cues can be ambiguous, but odor leaves a lasting impression. Predators that associate the shield bug's shape with that smell quickly refine their search image, excluding similar forms from consideration. This reduces wasted effort and allows predators to focus on more profitable prey. From an evolutionary perspective, this mutual adjustment stabilizes interactions. The shield bug survives. The predator learns. Energy is conserved on both sides. Environmental context amplifies these effects. On leaves rich in aromatic compounds, the shield bug's scent blends into the plant's chemical background, reducing detectability until release. On other plants, the contrast is stronger, making the warning more pronounced. The insect's success therefore depends partly on habitat choice, selecting plants that enhance both its visual and chemical defenses. The relationship between shield bug and plant is not symbiotic in the strict sense, but it is mutually reinforcing, each contributing to the insect's ability to remain unnoticed or unappetizing. From a distance, the scene appears static and uneventful. Leaves bask in sunlight. Insects move along predictable paths. Nothing suggests tension or threat. Yet within this calm, the shield bug stands ready, its body aligned perfectly with its environment, its chemistry waiting in reserve. It does not advertise itself like the ladybug, nor does it ambush like the mantis. Its approach is quieter, more conservative, relying on avoidance rather than confrontation whenever possible. This strategy is especially effective in ecosystems where leaves dominate the visual field, creating endless opportunities for the shield bug to blend in. In such environments, predators quickly learn that not every shape is worth investigating. Attention becomes selective, and the shield bug benefits from that selectivity. The insect survives not by overpowering its enemies, but by making itself an inefficient choice. When the day ends and light fades, the shield bug remains where it is, indistinguishable from the plant that supports it. If discovered, it will respond. If ignored, it will persist. The order of operations matters. First, vanish. Second, repel. The shield bug understands that survival is best secured by never being worth the effort. Stealth first, chemistry second. On a sunlit wall, a leaf edge, or the rough bark of a tree, the jumping spider pauses in full view of a world that believes itself unseen. Its body is small, compact, often no larger than a fingernail. Yet its presence carries a quiet intensity that changes the rules of the scene. Unlike many predators that rely on speed, venom, or overwhelming force, the jumping spider relies on something far rarer among invertebrates: clarity. It does not guess where prey might be. It does not strike blindly into motion. It looks, and what it sees is sharper, more detailed, and more informative than what most insects ever experience. The spider's defining feature is its vision. Dominating the front of its cephalothorax are large, forward-facing principal eyes, capable of resolving fine detail at close range. These eyes do not merely detect movement. They resolve shape, edge, orientation, and depth with a precision that allows the spider to identify prey, rivals, and even potential mates visually. Secondary eyes ring the head, providing near panoramic awareness and detecting motion from almost any direction. Together, this visual system transforms the spider into a hunter that does not rely on chance encounters. It hunts by sight, in a world where most creatures assume sight is a weakness. This ability fundamentally alters how camouflage functions around it. Many insects survive by becoming background, by exploiting the limitations of predator perception. Stick insects dissolve into twigs. Butterflies scramble outlines. Bugs advertise danger. All of these strategies depend on predators failing to resolve the truth quickly enough. The jumping spider is different. It does not process the world as a blur of motion and color. It inspects it. It tracks individual shapes, following them with subtle head movements that align its principal eyes like a pair of binoculars. Disguises that fool birds or lizards often fail under this scrutiny. The spider does not rush. Once prey is detected, it enters a stalking phase that resembles a miniature tactical maneuver. It adjusts its position incrementally, choosing angles that keep it out of the prey's direct line of sight. Movement is slow, deliberate, and precise. Each step is placed carefully, avoiding vibrations that might alert the target. The spider's body lowers, reducing its silhouette, while its legs reposition to maintain balance and readiness. This is not instinctive flailing. It is controlled approach, guided by continuous visual feedback. Distance matters more than speed in this encounter. The jumping spider must judge the exact gap between itself and its prey because its attack relies on a single decisive pounce. Too far, and the leap falls short. Too close, and the prey may react before contact. The spider solves this problem through depth perception, using the relative movement of images across its retina and subtle shifts in focus to calculate range. This ability, rare among arthropods, allows it to strike with astonishing accuracy. When the moment arrives, the pounce is explosive. Muscles alone are not enough to produce the necessary acceleration, so the spider employs hydraulic pressure, rapidly forcing fluid into its legs to extend them with sudden force. The leap covers many times the spider's body length in an instant. There is no warning arc, no gradual build-up. One moment the spider is still. The next it is airborne, legs outstretched, trajectory locked. Reaction time for the prey is effectively zero. Contact is immediate and final. The spider's fangs deliver venom that immobilizes quickly, preventing escape even if the prey struggles. Silk may be deployed to anchor the spider during the leap or to secure the prey afterward, adding another layer of control. The entire sequence, from detection to capture, unfolds with efficiency that leaves little room for error. This is hunting optimized for certainty rather than chaos. What makes the jumping spider especially formidable is its flexibility. It does not rely on a single prey type or environment. It hunts flies, ants, small moths, and even other spiders. It operates on leaves, walls, rocks, and human structures with equal confidence. Wherever visual information is available, the spider can exploit it. This adaptability allows it to thrive in environments where camouflage-based strategies dominate, turning those same strategies into liabilities. Predator-prey interactions involving jumping spiders often reverse expected roles. Insects that rely on being ignored suddenly find themselves observed. Those that depend on last-second evasive maneuvers are intercepted mid-movement. Even aggressive insects may hesitate, misjudging the spider's intent or distance. The spider's ability to pause, reassess, and reposition mid-stalk allows it to correct mistakes in real time. It is not locked into a single trajectory until the moment it chooses to leap. This visual dominance also extends to risk assessment. Jumping spiders recognize threats and avoid confrontations they are unlikely to win. They track predators visually, altering routes or freezing when detection is likely. This awareness reduces mortality and allows longer lifespans relative to many similarly sized arthropods. Survival here is not just about attacking effectively, but about knowing when not to engage. From an evolutionary perspective, the jumping spider represents a different answer to the problem of survival in visually complex environments. Instead of becoming harder to see, it becomes better at seeing. Instead of manipulating perception, it outperforms it. This shift forces prey species to evolve new defenses or accept higher losses. In ecosystems where jumping spiders are common, camouflage alone is rarely sufficient. Prey must add speed, unpredictability, or chemical deterrence to compensate. There is a quiet irony in this dynamic. Many insects invest heavily in deception, in perfecting illusions that exploit cognitive shortcuts. The jumping spider bypasses those shortcuts entirely. It does not rely on assumptions. It verifies. Its eyes cut through noise, resolving detail where others see texture. In doing so, it exposes the limits of disguise. No matter how refined a trick becomes, it remains vulnerable to a predator capable of seeing past it. As the spider finishes its meal and returns to stillness, the world resumes its background motion. Leaves sway. Insects pass by unaware. To most eyes, the spider blends into its surroundings once more. But this invisibility is incidental. The spider does not depend on it. It depends on vision sharp enough to make invisibility irrelevant. In a landscape shaped by illusion and misdirection, the jumping spider stands apart as the hunter that reads the scene instead of being fooled by it. Its presence is a reminder that camouflage is never absolute, only conditional. When perception evolves faster than deception, the balance shifts decisively. Camouflage fails when the predator has better eyes than your tricks.